Marching right along with our review of everything you know about mechanics, but looking at the angular versions instead. So today we're going to be looking at momentum. The regular linear momentum that we all know and love is P equals mv. This is a conserved vector quantity, and that gives it some interesting properties. You might be able to guess the angular analog. Instead of mass, we're going to have moment of inertia. Instead of velocity, we're going to have angular velocity. And instead of a P, you guessed it, an L. Where that comes from, I have no idea. But this is also a vector quantity, and it is also conserved. So we can say that the initial angular momentum equals the final angular momentum. And this is as long as there are no external torques acting on the system. There can be external forces as long as there are no external torques. So that can take place if the force is acting right on the axis of rotation. Also, angular momentum is conserved completely separately from linear momentum, so you can't convert one to the other. It's not like energy where you just have different types and they're globally conserved. These are independently conserved. As far as the direction of this angular momentum vector, it's the same as the direction of the angular velocity vector. So if we have a disk spinning in the plane of the screen here, and let's say it's spinning counterclockwise, then you'd wrap your fingers in that direction, and your thumb would be pointing out of the screen. That is sometimes denoted with a circle with a dot in it. So that would be the direction of your angular velocity vector, and it would also be the direction of your angular momentum vector. Conservation of angular momentum explains a whole host of phenomena, not the least of which is why figure skaters can spin so fast. So if you've seen them do, I don't know what they call these spins, but they'll start out with their arms outstretched, and actually their leg is usually outstretched here too. Here's a leg. And then when they pull all of those limbs in, they have increased their angular velocity by decreasing their angular inertia, their moment of inertia. And essentially I naught omega naught equals I final omega final because of conservation of angular momentum. And so if this guy gets smaller, then that guy has to get bigger. Also, you'll see divers, they'll pull their limbs in to spin faster, and they usually will extend out at some point to slow themselves down for entry into the water. Or if you ever watch those skiers, they used to call it hot dog aerials, I don't know if they still call it that, but they are constantly moving their limbs in and out. Even a snowboarder doing a 1080 or whatever, you'll see them pull their arms in to spin. Anyway, this is going on all over the place. It also is incredibly important in astronomy. One thing that can happen to a star as it dies is there's no more fusion in the center causing pressure to go out, so the star can collapse on itself. And it can create what is known as a neutron star. And a neutron star is about the size of a city, but you take the mass of an entire star and cram it into that size. So it's very dense, but it also follows this same conservation of angular momentum, and that can cause them to spin really quickly. So if we do a quick little calculation here where we say initial angular momentum equals final angular momentum, and we're going to apply this to our star. The moment of inertia for a spinning sphere is, I think it's 2/5, yes. So 2/5 times the initial mass times the initial radius squared, all of that is our moment of inertia, times the initial angular velocity squared. And then we've got that same factor because the neutron star is still a sphere, times the final radius squared. And that is going to equal our final angular velocity. Oh, not squared. Get rid of that. Now this goes away, the factor of 2/5, and we are assuming no loss of mass. Now a real star will probably lose some mass, but it will keep a whole lot of it. But for simplicity, we will say that the initial mass equals the final mass, so we can cancel those guys out. And we want to find the final angular velocity, so we can just solve for it like this, divide that final radius to the other side and just square the whole thing. And there we're in business, so we can plug in our numbers here. we're given the initial radius is 7 times 10 to the 5th kilometers, and because we have a ratio here, this is in kilometers and the final radius is also 10 kilometers, so those units are going to cancel out and you don't need to worry about converting to meters, so that is squared. Now we're not given our initial angular velocity in terms of radians per second. We're told that it spins around once every 10 days, so we can find that by doing 2 pi times the frequency. So the frequency is 1 revolution in 10 days, and then we can just multiply by 24 and by 3600 to get that to seconds. This thing works out to be 7.272 times 10 to the negative 6th. So if we plug that in here for our initial angular velocity, 7.272 times 10 to the negative 6th, and throw all this stuff in there, and we will get 35,633.8 radians per second. And if we multiply or divide by 2 pi to get it back to frequency, so omega over 2 pi is going to give us 5,671, there's my one, erase, okay, 71 revolutions per second. So this guy is cooking along over 1,000 times, almost 6,000 times every second. And they do find neutron stars that are spinning this quickly, so pretty incredible thing. And this has this idea of conservation of angular momentum, as I mentioned earlier, has lots of applications in astronomy. This is how we think stars and star systems, solar systems around stars form to begin with. Is you have this large nebula, this cloud of gas and dust, and it slowly collapses on itself due to gravity. And as it does that, it starts rotating, because if it was moving even a tiny bit when it was really large, by the time it collapses down, it's going to be rotating. And that's why everything in the solar system, for the most part, is rotating in the same direction. It all came from the angular momentum that the nebula had to begin with, and that was conserved. So there is that. Something else to look at, if we're looking a little more closely at this vector nature of angular momentum, right? We said L equals I omega. So if you have a person standing on a giant disk, I don't know where this giant disk came from, but anyway, if they're initially at rest, then the angular momentum is 0, and if they start walking in this direction, they are considered to have angular momentum because they are going in a circle. And so their angular momentum would be up, but we need to, just like with linear momentum, if we create momentum where there was none to begin with, we need to have momentum in the other direction to cancel it out. So what's going to happen here is the disk is going to start rotating in the other way, and if you point your fingers, curl them in that direction, then your thumb will be pointing down, and so the angular momentum of the platform will cancel out the angular momentum of the person so that we can conserve angular momentum. And where better to see this than on The Simpsons? So enjoy a little clip here.
Run, Ralph, run!
Okay.
Time to do what I've never done as principal. Something.
Skinner's spazzing out!
I'm not spazzing out. I'm using the principle of conservation of angular momentum to turn the container.
That is so cool. That's the kind of stuff they should teach in school.
We do teach it in school. You're too busy eating sugar snacks and horsing around.
He's right. Learning can teach you things. Education rules.
Alright, getting back to the real world here, we have one more example we're going to look at. If you have a person standing on a turntable and they're holding a wheel that happens to be spinning. Yes, we physicists like contrived situations. And I'm actually going to show you this in class though, so this is going to happen. And I'm not going to tell you the answer. I want you to think about what's going to happen if this wheel is spinning in this direction and it's got some angular momentum in the upward direction, and then you flip the wheel. What is going to happen? Dun dun dun. You'll have to wait and see in class. Alright, a couple other things. We want to look at the angular momentum of a particle in a little more detail. And we're going to start out Newton's second law. We mentioned can be written in terms of, that's uppercase P, can be written in terms of the rate of change of the momentum. And we can have a similar situation for torque. We can say the sum of the torques is going to be the rate of change of the angular momentum. And this is true in general. And if we want to look at a single particle, we can derive another useful expression. So if we plug in for our torques, R cross F, where F is the net force, that is going to equal, this is a vector quantity by the way, that's going to equal dl dt. And then if we pull this, we can write F as dp dt like we just did at the top there. Sorry, I was getting one step ahead of myself. Dp dt, all of that is still equal to dl dt. And then if we pull this r into this derivative over here, we're going to have d by dt of r cross p equals this guy here. And now if we take the integral of both sides, then this stuff goes away and we have r cross p is equal to the angular momentum. This is typically applied just to a particle because the dp dt doesn't make so much sense for a rotating object, because which part of that object are you talking about? So this is applied to a single particle. And so if you look at this as being a cross product, we said earlier that we can rewrite a cross product if we're just interested in the magnitude. We can say that this is rp sine theta, where theta is the angle between the r and the p vectors. And so that is going to give us the magnitude of L. Oftentimes this is written with a lowercase l for the momentum of a particle, and then capital L is for a system of particles or for an entire object. And this is the same thing as taking the perpendicular component of r times p, or the perpendicular component of p times r, like we saw earlier. So we get something that looks like this. If we have a particle just going around in a circle like this, then r is perpendicular to p in this case. So then you can just say that the angular momentum of that particle, L, equals r times the momentum, and the momentum is mv. So this is going to be a useful little expression we're going to have a lot for particles moving in circles. A couple other things. I said we were almost done. I lied. Sorry. Here's an example that this is one of the weirdest things about angular momentum, but it comes up a lot and we're going to use it. So if I fire a bullet and there is some super glue on the edge of this disc here, yes, amazing super glue, such that that bullet sticks to the edge of the disc, well, then we would imagine if there's no frictional torques that this disc would start rotating as it hit. And if it starts rotating, it's going to have angular momentum. But here we just had a bullet flying, so where did that angular momentum come from? Well, we have this little kind of cheat almost where we say a particle can have angular momentum with respect to a point using that definition that I just showed you on the other page, where L equals rmv, where r is going to be the perpendicular distance that we mentioned earlier, or essentially the distance of closest approach, because if it didn't stick, it would fly by, and that would be the perpendicular distance relative to that point there. So in this case it would be r naught mv. So we would say that that is the initial angular momentum of this bullet. I know it's not going in a circle, but we can say that it has angular momentum with respect to that point. So if we wanted to find, say, the rate at which the disk rotated, we would set that initial angular momentum, r0 mv, equal to the final angular momentum, which would be the angular momentum of the disk plus the angular momentum of the particle now on the edge of the disk. I'm not going to solve this all out, but the angular momentum of the disk is 1/2 times the mass of the disk times its radius squared. And then we can treat this as a particle, this bullet on the outer edge, so that is just going to be m. I guess I should call this massive bullet, right? mr squared is the rotational inertia. Oh, and we need our omegas here. So that's going to be the total rotational inertia, and they will have the same angular velocity, so we can just say that there's one final angular velocity here. And if we know all of these things, then we can solve for, well, all but one. We can solve for one unknown. These are going to be the same radii here. Okay, so there's that fun example. And another fun example is our good old Atwoods machine. And we already looked at this where we analyzed the torques acting on our disk, but we can also analyze this situation using angular momenta, again treating these boxes here as particles moving with angular momenta of L equals mvr. Kind of weird, I know, but it all works out, and can't argue with nature, right? So let's look at how we can get the same expression we saw earlier. If we start out with the sum of the torques equaling the rate of change of the momentum. So here we're looking at the external torques because we want the change in the angular momentum of the whole system, whereas before we were looking at the torque just acting on the disk. So since we're looking at the external torques, those are the forces acting on these boxes. So we're going to have gravity on box B times the distance from the axis of rotation, the closest distance from the axis of rotation, minus gravity on A times the distance to the axis of rotation from the force acting on A. And then we can set this equal to the derivative of all the angular momentum. So we're going to have to sum up the angular momenta of all of these different particles and disks. So here we've got, we're going to use mvr for this guy. I'm actually going to write it as mrv for a reason you'll see in a second. So that's for particle for box B. And we're actually going to add the angular momentum for box A because both of these would tend to make this disk rotate in the same direction. So they actually have angular momentum in the same direction. So that's going to be MA R0 V, and these are going to be the same V's because we're assuming this rope isn't stretching or compressing. We're also assuming it's massless, so we're going to ignore that rope. And then we need the angular momentum of the disk, which we can just say is I omega for now. So we've got this whole thing. This we'll go ahead and factor out the GR. So we've got MB minus MA times GR0. And here, if we take the derivative of each of these terms, M and R and I are all constant, but V isn't constant. And the derivative, the time derivative of velocity is going to give us the acceleration. So we've got mass of B times radius, not alpha, gives us linear acceleration because this was linear velocity, plus mass of A times radius times that acceleration. Now I for a disk is 1/2 m, I'll put disk R0 squared, and the derivative of that is going to give us alpha. Now alpha, like we wrote before, I'm just going to erase it because I don't want to rewrite everything, is A over R0. We can cancel out one of the R0s, and if these R0s can cancel because there's an R0 in every term over there, and if we're going to solve this for A, we just factor the A out of every term and divide, and we'll end up with the exact same expression that we had before, where we have the difference in the gravitational forces all over the total mass, except the mass of the disk once again only counts as half. So I don't know that that's really any easier than the way we did it before, but it's definitely a different approach and gets us there all the same. One last thing I promise, and this is a pretty cool demo to see, and I'll show it to you in class as well. If you're holding a spinning wheel out, so it's spinning this way, and if you wrap your fingers in that direction here, then your thumb will point out there, so you have angular momentum in that direction. And then if you try to lift this wheel up, we've got that expression that torque equals dl dt. So if you're pulling up on this wheel, it's going to tend to rotate up, and that's exactly what it would do if it weren't spinning. But a wheel that is moving up like that, if you put your fingers in, curl your fingers in that direction, your thumb will be pointing out of the screen towards your face, and so there has to be a torque out of the screen toward your face. That's the direction of the torque vector if the wheel is going to rotate this way when you exert a force on it. Because torque also equals I alpha, and that's the alpha as it rotates would be defined as coming out of the page. So the torque has to be in the same direction as the change in angular momentum, and if the angular momentum is here, that means the angular momentum has to come out of the screen, and that wheel, as you pull up on it, will not actually move up, it will move to the right of this person here. So we'll play with that in class. So that's all. See you next time.